So I know you guys want to hear a lot about the technology. That's really what you're here for. As you know, our core technology that we really were founded on is a technology we call BeamFlex. And we've actually started changing our name a little bit to something called adaptive antennas, because as you know, 11N has finally started doing beamforming, which is what our marketing folks, including myself, have called it forever. So when you listen to Victor, keep in mind we actually are separating the terms now between beamforming, being standardized chip-based, we call it chip-based beamforming, compared to adaptive antennas. So Victor has got a few presentations. I'm going to kind of run the clicker. So I'd like to introduce Victor Shtrom. He's a really smart guy. I have a man crush on him because he's so smart. And he's basically our RF designer. And so Victor, come on up.
Hello.
Hello.
Is this on?
Yes.
Why don't you
Okay.
run? I sort of wanted, it's going to be kind of cartoons and some of the stuff some people know and some people may not know, but the reason for wireless not be, so what happens when a wireless signal, you have multipath. You've probably heard that term before, and you may or may not know what it means or what it does. But that's why I have these simulations that I actually borrowed with pride from the geological survey, which actually there was, as you know, there was an earthquake in Japan, and these guys did a really nice simulation, and RF works exactly the same way as these waves do. And I just wanted to kind of go ahead and show you that. There's all the credits that need to go to the people that did the work. We just found it on the website and did it. So what this is what we'll call an impulse response. This happens at light speed in RF world. These are of course waves in the water. But what happens is you have something that causes the wave to happen, and then it goes and it bounces off, and whatever objects are in the way, they will bounce it in whichever way it's going to happen. So what you're looking at actually, so if you assume this is RF for a minute, well, keep going.
Sorry.
And if you stick an antenna in here, you can sort of see that the signal on it is basically going up and down. And that is what causes the unstable performance in wireless systems. Okay? And our fundamental DNA back in the old day when we started was IPTV. So that meant real IPTV. For example, a carrier gets the European Championship, football or soccer European Championship, and it's got to work. And it's not something that you can't cache it or anything like that, because it has to be it's real-time TV. So any time you have a dip or something like that, you would lose data. Okay. So this is signal level on an antenna, and every time it dips below a certain point, right, your throughput gets more or less based on where your antenna is in space. Okay, so I wanted to kind of show you that, and then I wanted to kind of show you actually to the thing we actually did ourselves, and to say, well, what does BeamFlex do, and how does it solve it? And this is this works for. Can you make it? Yeah, there you go. This is space. Okay, and what we're saying is, if you have a client, for example, anywhere within this space, let's say in some location, what BeamFlex will do is, if a client is over here, it will put a peak of this multipath where the client is. Okay, and we can do this on a per client, per packet basis. Okay, and for example, these are the deep fades. Anything 5 dB and below is in red. 0 to 5 is in yellow, and anything above 0 is in green. So you always want to put your signal, the highest point, the highest peak. The BeamFlex can do that. Put the highest peak of the signal where the client is.
So just to reiterate, this is a static environment, meaning that there's a client and there's a transmitter, and the environment is creating this. So
as you saw the waves from the earthquake, it's continuously happening. Okay, based on like I'm moving in the room, I've just changed the way everything bounces around. Your dog ran past your TV. The dog's presence changes. It creates a little island in that ocean of water, which causes ripples in various directions. So that is the fundamental problem with wireless, and this is the way to solve it at the physical layer or at the antenna layer, okay, is to basically change the way that the signal bounces coming from the antenna. So the joke is, you can move walls around or you can change antenna patterns, and we kind of think changing antenna patterns is a little bit easier. So that's the fundamental kind of reason for Ruckus being here, and that's our fundamental differentiation, and nobody else is doing that. And again, we learned very early on our fundamental DNA comes from doing IPTV. And what does that mean? Well, if somebody tells you your link is 50 megabits per second on the average, and you did 100 megabits for 1 second, and you did 0 megabits for the next second, you can say that's 50 megabits. Of course, that isn't something that you can watch. So we always look at what is the 99th percentile throughput or 99.9 percentile throughput. So the trick is what is the lowest throughput actually, and that determines the quality of service.
Andrew did a nice review on ZAP, which we very much appreciate. ZAP was developed for that. When we do testing of environments and we test our APs, we don't test them for an X-chariot. It's not that that's bad. That gives you nice average throughputs. What ZAP does is when you do it, especially command line based, you see these percentiles that Victor is talking about. And that's the number we look for, is a 99th percentile. What is that? What is happening there? Not on average, because on average is not really not really what we want. We don't care so much about average. We care about what happens 99.9% of the time.
We architect for the worst case.
So you may ask, what is the difference between what you're doing and what's going on in 11N with the 11N beamforming? And that's another very interesting thing. So what happens at 11N, the chip is doing the beamforming. So that happens at baseband, and you have, generally speaking, the competitors have static antennas. They're just sitting there. And the beamforming is, the 11N beamforming is the phasing of the different antennas between each other. That's the good news. The bad news is when you try to do multiple streams, you actually need those different antennas to have different streams on them. And you can't beamform different streams. Because in order to, when I say the word phase, that is the difference between the same signal, one signal and some delayed version of the same signal. So if you have, but 11N says, oh no, I want to do multiple streams, so the signal on this antenna and this antenna isn't the same. So you can't phase those two. So what it becomes is a trade-off between capacity, which is what the dual stream or triple stream. I assume you all know 11N. I don't have to tell you all that. Okay, so there's multiple streams, which is a capacity improvement, and then the beamforming is actually more of a robustness improvement. So there's a fundamental trade-off between the two. The semi-bad news is spatial multiplexing actually wants completely different paths. So the best way to do spatial multiplexing is actually to do it on both polarizations. So for example, if you're horizontally polarized, if one stream is going out on a horizontally polarized antenna and the other stream is going out horizontally polarized antenna and the other stream is going out on a vertically polarized antenna, you're guaranteed, there's no way sending the signal this way will cause the same thing to happen. Okay, so you're pretty much guaranteed a different multipath. The way 11N works is because you need to be able to tell the difference between the two antennas at the far end to be able to decode the streams, okay? And you can guarantee to have different multipath profile if you send one horizontal, one vertical, because they won't bounce the same. The probability is very, very low of that happening. So in order to do the best thing for spatial multiplexing, you need to do the cross pol. However, you can't beamform that. You need to beamform with the same polarization. So the two ways to improve the wireless link are actually diametrically opposed when it comes to how you come at it. So what Ruckus does is actually when we do our beamforming, BeamFlex is not really related to I could probably show it on that antenna a little better because this antenna has too much stuff on it. It's hard to see. Yeah. The way BeamFlex works is it doesn't actually. By the way, this is a dual polarized antenna. We kind of put some funny pictures on here. It's because there's a lot of websites out there that we've seen websites with 30 pictures of our antenna in various aspects and all that stuff, so we want to kind of camouflage it a little bit. So all this white stuff is just camouflage so that people can't take pictures and see what's going on, because we do have something what we think is fairly unique, and other people haven't really figured out how to
Luckily,
do
this
that
isn't
yet.
live, so no one will know that.
Well, whatever. Take a picture. I mean, you know, you can't see. That's why we do it. So anyway, what we do is we actually have this has several vertically polarized antennas and several horizontally polarized antennas. So for when you do the spatial multiplexing, and sorry, I'm jumping around, but each antenna itself can beamform by itself. So let me say it slower. With the chip beamforming and legacy beamforming systems, it's the cooperation between the antennas that forms the beams. But that cooperation between the antennas is owned by the chip, and it's owned by 11N trying to do the multiple streams on it. We don't require cooperation between the antennas. So this is one, for example, there are 3 cables coming off this for 3 streams, okay? So each stream can
I did
be...
that to mess with you.
Yeah, thanks. Now it's all stuck. Okay, so for example, this guy can be beamformed all by itself, okay? Independent. So what happens is the analogy for what we do is we beamform like a lighthouse. I mean, a lot of people say, oh, it's flashlights, and that's kind of easier to understand, but in reality, it's actually a lighthouse. So we have an omnidirectional antenna in the middle, and we can change the reflectors to form the beams, okay? So it does not require the cooperation from multiple antennas. It just says, oh, here's this, and here's how I have a mirror behind it, and I can rotate that mirror electrically, not mechanically. There's no mechanical components.
Do you guys have questions so far?
That's good.
Okay.
Is this too deep, not deep enough? Okay, all right. And again, we do it, there's a horizontal antenna on there, and I just won't talk, it's just there. And it's just kind of hard to see, so there's another antenna on there. There's actually 3 antennas on here as evidenced by the 3 spigots, okay? So when the chip gets a hold of this, it's going to use these 3 spigots together to make beamforming, while we do it on each spigot individually. So we have a forward path, this works for G, N, whatever else comes along to the chip. This is sort of an antenna, and then of course there's a control connector here, and then we select the right combination of beams to provide the best throughput. And our metrics are always throughput. That's all that matters is your higher level throughput, and that's what ZAP measures.
So just because I'm a not smart guy, so what is in there is actually valves. Am I correct? So there's little valves in there that open and close to send the signal different directions. Would that be an accurate analogy?
We have a way to turn a mirror into glass. Okay, so so we have, let's say it's sitting in a as an analogy, it's sitting in a glass tube, for example, and sometimes we can make some piece of that glass tube a mirror. So all of a sudden, it shoots in that direction. If everything is glass, then you have an omni, right? And then you take that glass and you stick some metal tape, let's say, on one side of it. That's going to create a mirror, so that's going to push the signal in the direction where, so the signal comes off the antenna, bounces off the mirror, and goes back, adds in phase. So that's, your headlights on the car and that kind of thing. That's what's going on.
Can we get video of the faces? I wish we could do that.
Am I making faces? I'm
No.
This is a scary amount of detail. I'm very impressed.
Am I okay? Thank you.
No,
Is that good or bad?
Don't take that the wrong way.
Okay.
This is really, really, really good stuff.
And it's all proprietary.
Right. So if I start reeling him in, it's because we don't want to,
Yeah. I mean, Anyway. We're pretty far along in this technology. I think other people are probably capable to figure it out. The good news here, and the value, a huge value of Ruckus is there's probably a bunch of people that can design the antenna, but actually, okay, so if I gave you a bunch of flashlights and you kind of instinctively go, oh, I'm just going to point it this way. Well, try to write software to point it that way.
Would I be correct in guessing that the distance from the antenna to the reflectors is very important?
You would be correct. Because it has to come and come back, and that has to be reinforced.
Precisely in the opposite, whatever.
Exactly. It'll come back, it'll bounce off out of phase, and exactly. You got it. Exactly.
So I know just from my level of here at Ruckus, it is, so what Bill Kish does, who isn't here, Bill Kish writes these algorithms, what Victor's talking about, which is what designs the software to make these decisions. And those are constantly improved. He'll think of new stuff, and I don't know how, but he does. and he thinks of new stuff, and he tries it. And we have a whole testing lab. We actually have 2 other buildings that we do just for testing, and just to find out if these new algorithms work, keeping track of clients better and keeping throughput better.
Victor, can you talk about how we select the best antenna pair for a given client and that kind of how it works, please?
I'm not sure exactly. Let me. So again, we're trying to maximize throughput, okay? And then maybe let me think what you're saying is, let's say we say, oh, we have 4,000 patterns, and if somebody would say, wow, how do you pick 4,000 patterns? How do you pick the one good one for each client, right? Because you're going to get, so there's a table, again, it's proprietary. There's a table. If I'm talking to you, I'm going to use the best patterns for you. And as you guys all know, Wi-Fi, it's on the human scale, it's at the same time, but on the Wi-Fi scale, while I'm talking to you, everybody else is quiet, right? So there's this protocol, the MAC, and all that stuff. So it doesn't all happen at the same time on the Wi-Fi scale. At the human scale, yeah, I can talk to you and you simultaneously, but of course, I'm bouncing back and forth. So when I'm talking to you, I got your set of antennas. When I'm talking to you, I got your set of antennas. And we actually don't need to know a whole bunch of those sets of antennas. We just need to know which one is best for you, and when the one doesn't work for you anymore, we need to figure out which one to change to, and et cetera, et cetera. And the analogy there for how we figure that out, and that's actually not an easy part. So there's the beauty and the defendability of Ruckus is we're at an intersection of 2 places where there's a bunch of people that can figure out the antennas, and there's probably a bunch of people that can figure out the algorithms, but they're not in the same building. They're hardly ever in the same building. And can I pick on Cisco for a minute?
Yeah, you can pick on Cisco.
Okay, so their hardware team, their hardware team's in Ohio, and their software team is here, and there's just no way you can do this.
Is that the Bill Victor team?
Being in Ohio, well, Bill and I
their
talk.
offices are 3 apart.
Bill and I we generally we spend a lot. We talk to each other only about this. And that's kind of what we do, because we're constantly hey, how do we do this? How do we do this? So, long story semi-short, how we do it is actually, again, very proprietary, but let me give you an analogy. And what happens is, like, for example, if there are elections, right, in the United States, and there's, 150 million people that voted, and you're getting the results 10 minutes after the election ended, well, they didn't call 100 million people. They just called they decided that the 200 people we call is going to be representative. So we know roughly within very tight margin of error, whatever they call that this guy's going to win, right? Unless it becomes 49.99 and 50.11, then it breaks. So it's a statistics problem. And I wish I'd listened more in my statistics school. If there's a statistics teacher out here, I should have listened a lot more. But that is statistics is what we used to call it back in college. Statistics is what it was. But all of a sudden, man, I tell you, it's like useful. It's just one of these things where, and actually I listened enough to to get the gist of it. But Bill and I are sitting there constantly, and actually that's kind of a realization we came to very early, that RF signal, because of this waviness and all that, it becomes a statistical thing, not a DC direct current. It's not a steady state thing. It's some statistical thing. So there's some probability of it being here and some probability of it being. I won't. Now you guys are going to go whoa, but it's a probability game, okay? And that's how it works. And if the numbers are large enough, then the probability works. You know what I mean? I mean, the casino's going to make money off of you, each and every every time. Every once in a while, they're going to lose, but you go to Vegas and you see all these big buildings. Well, that got paid for by the people that so that works. Okay, so that's why I digress a little bit, but statistically works, and that's kind of how fundamentally it works.
Do you want to show this? We
have
now a little bit of time.
Possibly the question is in your mind. Possibly is okay. Now once the chip beamforming comes along, what are you going to do? And what are the gains, and how does that work? And so I entertain myself with Excel a little bit, and so this is kind of, so it's maybe a little bit hard to look at. This is a BeamFlex. So and these are real actual measured patterns here that we can make. Okay, so this is a BeamFlex pattern, and if you could tickle this guy. So if this guy just points to where the client is, just for this is kind of a little bit of it's reality, but just kind of. So if you keep tickling it, boom, then the BeamFlex pattern changes. He says, oh, maybe that's the best client for him. That's the best client for him, right? So that's what's kind of happening, okay? Now, if you come over far enough and you say,
I'm doing my best, man.
you can stop here. You can stop. So let's say the client is over here. Now the BeamFlex is doing this. Now can you tickle this guy? So now the chip.
I was just going to ask, how do you know if the client's at 5 o'clock or 2 o'clock? How do you get the location of where the client is in relation to the antenna in order to direct the beam?
Because we're looking at throughput. We're saying what is the beam that's going to result in the best throughput. Okay, the beam doesn't know it's 2 o'clock, or actually we don't even know what time it is because the thing isn't. I don't mean to be a smart because the thing is not. The thing doesn't have that, right? It's a.
I'm saying, but in relation to where the access point is, it can only know, like, at the RF perimeter what the signal strength is that the client has. So how do you know in which direction it is in relation to the access point?
We don't use, no, it's not exactly true. This is the statistical piece. We don't use signal strength for almost anything. That is, it's a really weird thing to tell people, but signal strength has very little to do. And okay, let me rephrase that because you guys are looking, what? In the licensed spectrum, signal strength is of value. In the unlicensed spectrum, there's so much interference, there's so much other stuff going on that just signal strength alone is very much devalued. So what we do is we look at throughput. So there's this probing, again, back to the Obama analogy or whatever, back to the, we have to probe a few and say, oh, okay, that's the best one for you. So
it doesn't tell you where the client is at. It tells you what beam is best for it.
Yeah.
So right.
Right.
And those are sometimes not very different things.
Different elements to figure
Yes.
out which
Correct.
Yes, but we do it again. But we do it very quickly.
It's not like a physical thing. You're just trying to pick the antenna pair that seems to work the best.
So
Yes.
you remember what?
It could be a.
You don't care spatial relationship.
It could be
really.
something
Right.
that bounces off a wall and delivers the
What-
best.
You remember what Eckhouse said that it takes a little while?
Yeah.
They were a little off on that. It's actually quite quick.
We can know very, very quickly which one is better than which. Again, like I said, instead of trying 4,000 pattern, we can know very, very quickly because statistically we know which ones it ain't.
You take a statistical sample and say, okay,
And then we start tightening.
And we know how we know how correlated they are. We go, if it's this one, then it's this one, this one, this one, this one, this one, right? If it's this one, then we know it's this one, this one, this one, this one, right? You see what I mean? That's how we pick it, and we can pick it very, very quickly because if we can estimate.
We can just take it quickly.
You already talked. We can estimate. We can estimate very. The thing that's really, really critical to all this is estimating throughput very, very quickly, and we can estimate throughput almost instantaneously without actually running the test. Okay, so that's the beauty of it.
Yeah.
Yeah, now you're impressed.
So not only do you guys make good antennas, but you have mad Excel skills.
Can you flip this guy around a little bit?
That's
just
Chip.
keep. So this is what BeamFlex is going to do, and this
Right,
is
the
what
right
Chip
one.
is going to do. Just keep going until
Right, the right
until you get to here. So I don't know if I think I answered the question.
So
Keep going. Keep going. Keep going. Keep going.
I'm
keep
clicking
going.
like I can, man.
So the chip's altering based on the direction of the client that's figuring it out.
The chip actually does it by sounding the channel.
Right.
It actually says, you guys again read this, it says, hey, what you got? And then you actually send me the steering matrix back.
Right, because that's what HP was just saying to us too. They had to have this thing on the client to.
It's explicit.
Atheros chip
Right.
set,
Yeah.
yeah.
Right. So I send it to you, and you tell me what the steering matrix is. So you tell me what phase shifts to apply, and this happens on a subcarrier. Again, I can go as deep as you want, but I'll spare you the details. So every little subcarrier, there's 64 subcarriers, and every little subcarrier has its own phase that makes it happy, and you tell me what that is. So you send me the steering matrix. That's explicit feedback. Implicit is kind of gone away. It doesn't really work. There's very reason. I can tell you
It
why.
hasn't gone away. Somebody still implements it.
Well, let me tell you why real quick. So it kind of, and I'll try to make it short. So, my mouth is talking to your ears, and your mouth is talking to my ears, and that ain't reciprocal. The channel is once it comes out of my mouth, yes, but my ears. What if I'm a little deaf? What if I'm, So the piece of circuitry inside the chip, you're talking to the receive of one end and the transmit of the other. And if you kind of look at it, they're different. The channel is the same, but the chip doesn't see the channel. The chip sees the channel plus the receive chain. it sees the transmit chain of you and the receive chain of me, right? And then I have to, based on that, I have to do the transmit chain of me and the receive chain of you.
So I kind of have to
it-
keep us on time. Here's one thing I want you to point out, Victor, because Victor and I were talking about this as he was educating me. Can you point out the difference between this, which is the chip beamforming, out of phase, is that correct? Or this is where they didn't want to
Phase,
send it?
well, the phase, yeah,
They didn't want to send it. They're trying to send it this way, but they had something happen over here. Is that correct?
Yeah, it's a combination of the two. So basically, the combination of the two is what results in this. So you get the gain from that. If it was just chip by itself, you'd have to tweak it some more. The other possible issue with the chip beamforming, again, it's gonna be kind of hard to explain, but I'll try to keep it short. What happens there is it doesn't know left from right. Okay, so if you have two antennas, can I draw or is that?
Yeah.
So if you have two antennas, okay, then there's a symmetry that gets set up. So the way the chip beamforming works, and you probably know about this, right? It's a delay. So if I send a signal from here, right, the thing says, oh, it arrived here just a little bit before it arrived here because it had to go a little bit that much farther. Okay. Well, guess what? If I send a signal from here, I can't tell the
It's
difference.
the exact same thing. Yeah.
So, and the way the universe works is, oh, so if you want to try to make a beam here, guess what? You will have to be making a beam here. So half your energy is going some place where you don't necessarily want it to go. Okay? And actually, BeamFlex having a dynamic beamformer on top of that actually prevents that other lobe. Because if I actually make if I make the BeamFlex beam on this guy, then this doesn't look the same as that.
And that's what's shown here. So this purple is the chip, and the black is the combination juice. So the BeamFlex antenna took it away from the client.
So are you using the third antenna on your thing in triangulation?
Triangulation is something else. No, we have three chains that are independent. So we have three of these lighthouses that are all sort of turning. Again, then you have to kind of visualize one that's turning. There are different polarizations, and then we just kind of say, again, this thing is this thing is like at the very top. It just says which combination of this is going to get me the highest throughput, and that's what I'm going with. So the trick is which combination, and how do I quickly find it, and how do I know when things start to degrade? How do I know what the next one to go to is, right?
You're just measuring the phase variance between the different elements.
We actually don't. The chip does that part.
Right.
So the chip sounds. I sound to you. You sound back to me. You tell me what the phase shift is,
That's
and
what I mean.
yeah,
Which is just
the chip is doing that. We don't do chips. The Atheros people and the Broadcom people and those people do all that work for us. So we're standing on the shoulders of giants, and we're free from all that complication. Well, there's another 3 billion. Atheros got sold for 3-some billion. That's the value they bring, and we're just standing on top of that.
You're adding the value with the antenna selection.
Right, and
polarization.
right. Among other things, we're not just an antenna company, but I'm,
What's your typical gain?
performance gain. See okay, when you say antenna gain, I can tell you that, fairly easy. We could do 6-7 dBi. I mean, the other thing is kind of when people say, what's your typical gain? Well, on that guy, 7363 was specifically size constrained and all that. And I guess, I don't know if you bust that guy open, it has a different set of antennas. So long story semi-short, that guy has about a 4 or 5 dBi gain. This guy's closer to 9. So it depends how much space you give me. I give you the gain. You give me the space, I give you the gain.
So
I don't
one of
get
the things-
space though.
So one of the things I want you to talk about, since we have very little time, is the fact that beamforming like we do, adaptive antennas is not just about range, right? We're not a range company. It was really cool in the beginning, but that isn't what it is.
Right.
So one of the big pieces is where you don't send a signal, right? So can you talk about where we don't send signal?
Yeah, let me talk two things. I'm going to augment what you just said. Thank you. So where we don't send signal, I will get to. But just so you guys understand, people they misuse beamforming, and we're not going to do that. What we're going to do is we're going to say, here's the deal. When you go out, and if you don't have beamforming, right, you have some edge of cell, right? So you go as far as you can, and now you can barely see the beacons, and there you are. And man, if you tried to send data, you'd be barely sending, you know, a megabit, and if you had a, you know, if you're doing 1 megabit per second, which is the lowest rate, let's ignore like all the overheads and all that. Let's just do the easy math. 1 megabit per second, you got a megabit file. You're basically on the link for a second. Okay, but so that's what people do without the beamforming. However, once you add the beamforming onto it, actually that edge of cell, where let's call that useless. Okay, you know, where you can barely, where you're sputtering. And by the way, while you're trying to get your second file, everybody else has to be quiet, and you're creating a lot of interference. Again, Wi-Fi is about capacity, not so much coverage. So at the edge of cell, though, once you put BeamFlex on top of that, now you've got the 4, 5, you know, 6 dB gain, and that's just in the antenna gain. There's also gain because you're not doing the fading, right? Because you're eliminating the fading. So there's the statistical gain that goes on top of the antenna gain. So there's this measured antenna gain where you can go in the chamber and measure the pattern. That's one piece of gain. But the actually biggest piece of gain is from this wavy, gravy situation I was showing you. You don't have the troughs. And that's another big piece of gain. And that could be as much as 10, 15 dB. I mean, basically, statistically, Rayleigh fading, 10% of the time you're 10 dB below, 1% of the time you're 20 dB below. So again, I can't answer that question with one number, but statistically, 10% of the time we help, you know, by let's see, yeah, 10% of the time we help by 10 dB.
So your point is that at the edge of that cell where the guy is, you're going to get a higher data rate because
Throughput,
you're doing something,
yes.
higher throughput.
It's useful.
Right. So,
It-
so
it-
it's not so much the range of the signal, but it's how much that guy can do now at the edge of where it was shitty before. Now it's going to be not shitty.
Yeah, we extend. So if you're at the very end, you're at the very end. You're almost dying. By definition, you're almost dying. But however, once you put BeamFlex into it, now you actually have useful. That edge of cell is actually useful to you, as
And
opposed
this
to
works
being
all
useless.
the way up, unless you're in a Faraday cage RF chamber. This works all the way throughout, not just edge of cell.
Right,
That's
but
why
the
we tell
improvement-
our customers, and you guys, when you use our gear, don't test us in a very clean, you know, on Marcus's farm in the middle of 20 acres that has nothing else. We want it tested in the middle of
I have an example of that.
downtown.
I actually have some of your APs and I've done some testing with them, and I have also like an air horn jammer, and like I test it with other APs, and like my throughput, I jammered like my client doesn't work anymore, basically, and then I test it with one of yours, and because of the gain and the, you know, everything you're talking about, I didn't notice it almost. I mean, I actually did this test with an air horn, and I didn't know what.
The other thing's a disaster.
Yeah, and
It's a killer.
I have an air horn and I tested it. You know, I tested it with other competitors' APs. My throughput sucked, and then I tested it with yours. And I'm like, oh, I've still got this thing.
The problem is a lot of environments that we're in are an air horn, right? You're in downtown X, and it's almost that bad.
So let me answer the second part, which is actually what you asked. So the other thing is, in a system, when you're, again, it's about capacity. So if you have, you know, 50,000 people in a stadium, you know, and everybody wants their piece, actually there's this temporal aspect to interference, right? So I want to give you the highest possible phi rate so I can get you on and off the link as quick as possible, right? And then I also don't pollute, so I'm not shooting in this direction where you ain't. You're over here, and I want to shoot to you, and then there's some other person who deserves his throughput, but since you know, since if you had an Omni, actually I should have put another, I just want to keep the number of things down, but imagine you have an Omni, right? That has no help. It's shooting in all directions. Even though I'm talking to you, there's some poor guy over there that also wants a little bit of data, but he's in the time that I'm talking to you, he is that's not available to him. Okay, so there's this capacity angle to this. If you look at it from the temporal side. So again, the point is, and throughput means, again, it's kind of obvious, but maybe not. You know, throughput means I get on off the link faster. That's really another value for the same amount of data, right? Does that make sense? So if I send 1 megabits at 1 megabits per second, I tie up 1 second. If I send it at 54 megabits per second, I tie up 1/54th of a second. So boom, boom, and you can have you can have the rest, right? So that's kind of the gains. Is that?
So part of the answer that I'm hearing from the way you explain it is you're not wasting energy by sending it in the wrong direction. So you're able to get better throughput because you're focusing the energy more to where it needs to be.
To put it in my terms, we reduce and sometimes eliminate co-channel interference.
The radio
Right.
fog, the
Right.
fog.
So in high density, where you know a lot of APs do a lot of damage to each other, I said Wi-Fi is its worst interfere, and it is. It's true in most environments. We reduce that, and that's that's it.
Yeah, at the fundamental level, we've been doing what is now sort of becoming, there's this, obviously LTE and there's a self-organizing networks concept. We've been doing self-organizing networks for the last 8, 9, I don't know, too many years. So we've kind of, again, we got thrown into it early on and we said, okay, how do we deal with this? And that was our answer.
So I want to leave a few minutes. We are tight. I apologize, Victor, because
That's fine.
I know people love you, including me. But if you have any
Easy.
last questions for Victor before we put on someone that's not as smart, which is me, then please ask them.
Yeah.
Do you have any webinars or that goes into more details?
I'll tell you this.
We do.
We don't go into more detail, actually, in a lot of ways. And hopefully you guys understand the reasons. Victor is one of those guys it's rare. So we don't go into a lot of detail because there's so much we do proprietary. And
There is some video
property.
of me someplace.
yeah, we actually did put that up on the internet.
That goes through this in about this detail and maybe a little bit more that's available.
It's on our website, right? You should be able to
Yeah,
get to it. Yeah, if you can point it to them. But yeah, again, we sort of we don't want too many people knowing about this because it's kind of again, both Bill and I came from different backgrounds, and again, it's this intersection of things and once people kind of figure it out, it's like they'll be on our tail. But hopefully, we're far along now to where, and actually, that's why I'm talking to you. If it was initially, I'd be like,
Well, one of the big
yep, mm-hmm.
One of the big benefits, he didn't mention that it's implied in kind of what he's saying is that because we're doing, we're focusing the energy, we're picking the best data rate for a given client, we're getting people on and off the network faster, and that's good when it's a shared medium when you want to support a bunch of users at the same time, because people always ask us, how many concurrent users does your AP support? Well, it's a matter of how you optimize the spectrum, because there's only so much spectrum. Spectrum is your limited resource, so to the extent to which you can get people on and off that spectrum faster, you'll be able to support more users. And because we pick the best data path, and we can neutralize interference that causes packet loss, we can ensure that we can get users on and off that medium much, much faster, so that we can get, so more people can get on the AP faster. So that's one of the really beauties of the technology that lends itself well to kind of the environment we're in, where you have a shitload of iPads and iPhones now that are all trying to bang on a single AP.
We actually had a software limit of 100 associations simultaneously, and we had customers repeatedly hitting that and trying to go beyond. We actually had to do software upgrades to go beyond that because of real life situations. Marcus, you had a question?
Well, I've heard the argument against it that, hey, this is a downlink only technology, right? Or is there an uplink complement? And if there's not, it doesn't matter. If you're using the medium more efficiently, downlink, is that good enough?
Let me answer this question. By definition, beamforming is a downlink technology. However, the really good news is on the uplink, you know what you're hearing, so you know how to best combine, and that's called MRC, maximum ratio combining. So there is a reciprocal relationship, but beamforming is a transmit thing. When you're beamforming, you're transmitting. So it is by definition a downlink technology. However, on the uplink, since we do have both, so in addition to, here we go, in addition to the waves, the thing when a signal bounces off various walls and everything else, it actually depolarizes also. So you actually don't know what polarization you're at, okay? If you use your iPhone like this, it's going to be, it's not an iPhone as you can tell, but...
I have enough money for once.
The antenna is horizontally polarized. There's one down here, and you probably heard about this problem they have with that, but that's okay. They got it solved. God bless them. It wasn't that big a deal. But anyway, so if it's horizontally polarized this way, but if you happen to be watching YouTube, then it becomes vertically polarized, okay? And if you have depolarization, how do you deal with that? And what we do is we have PD MRC, which is polarization diverse MRC. And again, without getting too mathematical, what that means is we can catch it in this direction and we can catch it in this direction. So no matter, I guess I should do the full, So no matter what angle, so if the multipath depolarizes the signal such it's this way, we'll catch this piece and we'll catch that piece. So we'll catch this and we'll catch that. And if you do the vector addition, which MRC will do, you get the whole guy. Okay?
So when you see our competitors doing omnidirectional antennas that spin around, that's when they're starting to do it.
But if you only have you only have vertical polarization, let's say,
Cool, actually.
Leslie Speaker.
if you only have vertical polarizations, you can only catch this. So you have this guy, right, and he's this long. I'm
You're
not.
actually going to make it 12 centimeters.
I'm not a drawer. Then you only get this piece of it, right? So you lose this chunk is gone. Okay. So what we do is what we do is called PDMRC. So on the receive we also have gain, but that's in the chip. Okay. There's many reasons. I'll spare you the details of why it has to be in the chip. Because again, that's actually the easier piece. And again, the difficult piece about beamforming is when I beamform to you, I have to know how you hear. Not how I can talk all day long, but I have to know how you hear, and that's what I have to optimize. When you're talking to me, I can do that myself because I'm the listener. Okay? So it's actually, on the uplink, it's actually a lot easier, and that's why MRC's been around for a while, maximum ratio combining, and there's various ways to do that. So again, in 3 words or less, maximum ratio combining is beamforming, but on the receive. People don't call it that, but if, the academics, nobody will puke at that and say, yeah, okay, people don't use it that way, but yeah, that's what's going on. You're combining a signal, but you're hearing it, okay?
From the client side, right?
All right, one last question for Victor. We got other stuff. I apologize. We need to pay for more time next time.
It's expensive.
I don't remember getting any money.
One more question?
Is there a possibility of doing the same kind of technology that you're doing with the AP from the client side and improving the
If
client
people
side
want to buy it.
The issue there is, let me see your iPhone again real quick. Did I steal it? No. The issue there is, I could just see that meeting that, when Jobs was alive, I can just see, it's got to look like this and it's got to look like that and everything is great. And then the poor antenna guy says, where am I going to put my stuff? And
That happens here.
and he says, why don't you put it on this little metal thing on the outside? And the guy goes, and he goes away. So long story semi-short, I'm going to have a really hard time doing the right thing with the antennas because this is so, every, fraction of a millimeter is spoken for, and I ain't it. I'm not the guy that, Jobs, God bless him, he's dead, but he wasn't going to give me any room. I just don't see myself walking into his office and saying I need a little more room for antennas. That would be a very short conversation.
Put an external lead to the dome and just be like, here's your
The problem on the client side, on the access point, we own it, and that's great. The problem on the client side, we'd have to work with somebody else, and they would probably be a little less receptive to us mucking with their let's call it a geomechanical problem and a business partnership problem, which raises the bar.
And we already do that to Victor. He's given a form factor like this, and he has to go invent antennas to make that work. Otherwise, we'd have an access point this big, and it would nuke people on the way by.
Thank God the Ethernet jacks are 500 mil, because they can't make it smaller than that. At least the Ethernet jacks are and that's what that was. Make it thin, boom, and the Ethernet jacks are what determines the thickness of that AP.
Oh, this one?
Yeah, that little white guy. It's a 7363. I'm sorry, I'm pointing at that. Yeah, him.
The stuff on the table. All right, Victor, thank you very much.
Thank you.
These are great.